Okay, this is the review for the second half of the Real-Time Digital Signal Processing Laboratory course at the University of Texas at Austin for the spring 2014 semester. Now, the second half of the class builds on the first half. You'll be tested on the second half, not the details of, say, Parks-McLeod algorithm or something from the first half, but knowing about FIR filters from the first half obviously plays a big role in the second half. So today will be a review of midterm, being ready for midterm 2, next lecture period. Our introduction will go back over the signal processing building blocks, and we've done a lot of them. We've done FIR and IR filters. We've done data conversion, which includes quantization and sampling. We've looked at rate changers, upsampling and downsampling, and then more generally, decimation and interpolation, if we add the filters into the story. And then we'll look at some communication system examples from the second half of the class. The theme through the semester has been design trade-offs in signal quality versus implementation complexity. And way back in the beginning, I asked you about measures of signal quality. Back then, we talked about signal-noise ratio as a starting point. But now you've seen other measures. We've talked about symbol error rate, bit error rate. We've talked about throughput, so different measures. So signal-noise ratio is the first place to start because that's sort of application independent. And then you would then go beyond that and expand it to include things that are specific to your application. Complexity, we focused on the number of multiply adds per second, ultimately. Amount of memory, storage, how fast that memory is accessed. It's been our big, our primary measures of implementation complexity. All right, so let's go through this. So for the introduction, you know, this is way back now. This should be pretty good basic stuff on this slide. So for the algorithms we've looked at for this semester, we've dealt with multi-rate processing, so upsampling, downsampling, going from sampling rate to symbol rate and symbol rate back to sampling rate. We've talked about changing sampling rates in digital to audio converters. Lots of different applications. Talked about, you know, increasing the size of images by adding, you know, doubling number of rows, doubling number of columns. These are all multi-rate examples where we change the sampling density of the signal. We looked at local feedback, like IR filters, feeding the input back to the output back to the input locally, just in the filter, not in some larger system. Adaptive filters also had some. So we had local feedback for the signal. We've also had local feedback to update coefficients of the adaptive filter. We've looked at iteration, and that's probably a little more the adaptive style. We've looked at phase lock loops, all kinds of things that have been adaptive, automatic gain control, equalization, symbol time and recovery. So lots of different things we've looked at adaptive, where we iterate over some training signal to update coefficients for our subsystem, the subsystem, whatever we're working with. Signal representation, we looked at bits and symbols of bits, or symbols are just groups of bits. Our symbol amplitudes have been real valued, but we can also think of them as complex valued for quadrature amplitude modulation. We have an in-phase component and a quadrature component, and so we can think of that as complex valued, with the in-phase component being the real part and the quadrature component being the imaginary part. Done a lot of work with vectors and matrices, probably more so with vectors than anything else. Vectors for storing current and previous input values, vectors of filter coefficients. We've looked at vectors just as a means to do a finite length simulation over some number of time steps. Matrices not as much, but we certainly have seen them. You've seen the matrices at play in the least squares equalizer in homework 7, so they're still at play. But all of our vectors and matrices have been scalar data types, mainly real valued. The algorithm implementation, our algorithms we've looked at have been dominated by multiplication additions, which we tend to just abbreviate as multiply accumulates. And then we've looked at, talked about throughput, how fast can we get data through the system. Now we look at some common themes in our algorithms. What we don't need is we have never needed recursion in what we've done. There's no tail recursion. It's just it's iterative but not necessarily recursive. Where a function calls itself would be recursion. And if you remember, we looked at different visualizations. This was another measure of signal quality. This was, instead of SNR, this was bit error rate. This is just a plot of bit error rate versus SNR for different, probably different modulation sizes. But also I-diagram was another measure of signal quality, empirical, easy to use. Again, way back to the first half, just because we use it in the second half. We've talked a lot about, visual representations of our algorithms and block diagrams. So we've had different ways to represent gains. Gain by A naught, either one's fine. Delay, oddly enough, written in the Z domain, even though it takes place in the time domain as a function. We use these as building blocks in a finite impulse response filter. We need these for pulse shapers, match filters, and so forth. Go ahead. Yeah. Yeah, they're in the reader too. Okay, this is midterm 2 review. Sorry. Yeah. I think it's numbered as lecture 26. It's all there. Go ahead.
That's just like an arbitrary operation. Like it could be plus, it could be.
Yeah. So this one here is the arbitrary, operation that takes two inputs and produces an output. Add, multiply. Point-wise stuff. All right, now the FIR filter is kind of nice. It's always stable. Each input sample produces exactly one output sample. And it really, the architecture for digital signal processors were developed to do this as fast as possible and as few instructions as possible. So multiply is high speed, so you multiply, add operations. So multiply is high speed, adds high speed. I have to maintain a circular buffer along the delay line. So on my processor, I want modulo indexing built into the addressing mode for speed to access in the circular buffer. I also have a down counting. Right, so here's my input-output relationship. It's just a for loop, a down counting for loop, usually for faster implementation versus up counting. So I down count this placeholder variable, little m, and just do multiply add until I'm finished. I can also think of this as a vector dot product of a vector of the coefficients of my filter and a vector of the current and previous input values. So the DSP processors are also good at vector dot products, matrix vector calculations as well. It's the same formula. IR filters, again, we haven't used that as much in the second half, but they're there. We've talked about them in symbol timing recovery. A to D converters. We'll have the anti-aliasing filter, and the A to D converter will be IR, although analog and continuous time. The carrier detection is IR. So it still shows up, just not quite as common perhaps in discrete time in our example applications. In Lab 7, IR filter in the audio for Lab 7. So you get some nice audio effects with feedback. Okay, so this is our IR filter. Again, each input sample X produces an output sample Y. Like the FIR case, but now we have local feedback within, from out somewhere in this system. So here we feedback the output in our calculations. And the problem with that feedback is that we can never, or it's very rare that we could implement this in exact precision. So we lose something because of feedback. The word length in this feedback loop will grow to capture the calculations in exact precision, and that growth is without bound, so we wouldn't do it in practice. So we limit, either it's a single precision float or 16-bit int or 64-bit float. So we're always going to get truncation here as a result of the multiplication and a result of the addition, and this is going to introduce quantization error. And that's something that is just a limitation in IR filters. We really, once we implement this, can rarely keep the LTI property because of this. Now, also to actually separately from that, just to represent the feedback coefficients, we also run into trouble pretty quickly, because if we pick a IR filter with a lot of order, high order, 10th, 12th order, and we expand this out to direct form, then we get perturbations in the where the poles locate, because we're going to multiply those out to get the coefficients. And so generally we want to implement this in factored form. Lots of filter structures out there, but the ones we care about are certainly direct form, but we like to use small orders. The one that we implement, we typically will use cascaded biquads or a lattice. Now, lattice we haven't talked about, but just to put it up here for completeness. So generally cascaded biquad. So in midterm 1, you design some biquads in midterm 1. I suppose it could happen, to something in communication systems. For example, an equalizer that's IR, or a notch filter to get rid of an interference source that could happen in midterm 2 for pole zero placement. Data conversion. All right, so now this is the really lecture 8 and lecture 10 put into one slide. It's a lot in one slide. Okay, so for the analog to digital conversion, the theory says anti-aliasing filter, continuous time in analog, followed by sampling and quantization. The quantization will go to B bits. In lecture 8, we analyzed the quantization error, same as the quantization noise. And the key in the system, what we'd hope to do is we'd like to choose the number of bits to either meet or exceed the thermal noise that's in the system. If we don't use enough bits, then what we end up doing is we end up having the quantization noise greater than the thermal noise, which we could do, but then we add more noise to the system, and that's usually not preferable. Sometimes it is, in odd cases, but for ADD conversion, from input to output for the ADD converter, we would really like to have the converter matched in terms of quantization noise to the thermal noise in the system. All right, so what that will mean is if we're equal to the thermal noise, if the quantization noise is equal to the thermal noise, how good are the bits? Are all the bits good down to the least significant bit if we match? If we match thermal noise with quantization noise, they're equal. Same noise floor. Are all these bits good, or do we still lose some bits? But I've given you already that we matched. So I've picked the right number of bits so that the quantization noise floor has matched the thermal noise floor. Well, it's more than that. So here's the SNR and dB, and it's we derived this in lecture 8, and some constant plus 6 dB per bit. And I don't remember the 0.02, honestly, so I just really remember 6B. It's accurate enough. So if I've picked enough bits to match the noise floor, then I'm good. All my bits are good. If I pick more bits than the noise floor, if I pick more bits, which gives me a higher SNR, then I'm now quantizing noise. The last so many bits, the last so many least significant bits, are capturing the noise.
You're saying like while keeping the SNR pretty much at a constant, if you try to add more bits with the same SNR, you're forcing some of the noise to.
That's right. That's the way to look at it. So so in the system, I have some thermal noise. I mean, in theory, the noise floor is flat, but in practice, it's not. So I have a noise floor, and it should be symmetric about the two. Do my best. All right, so this is my noise floor. And then my signal strength, we can just say is, we could say 0 dB. My noise floor is way down here for the thermal noise. So what I'd like to do really is to have the quantization noise match that if I can. And it's okay if I exceed this. If I have more bits than the SNR would support, based on the noise that's already in my system, then fine, the last 2 or 3 bits or whatever is just noise. And now this is the case for your data converter in lab. We went through this. So I have a 16-bit data converter in lab that you're reading from. The A to D, this is the analog interface chip, the AIC chip on your board. You read 16 bits from the A to D converter, but only the first 13 are good. And when the upper 13 most significant bits are accurate, the low 3 bits are noise. But it's easier to read 16 bits than 13. What do you do with 13 bits? Everything's working with multiples of 8 bits internally on CPU and in memory. All right, so that's the and the reason that we talk about the difference between the signal level and the noise level is because in our SNR definition, again, this is 10 log 10 of signal power over noise power, using properties of logs, you can, since we have a division inside the argument of the log, it's just a subtraction. of the log of the numerator and the log of the denominator. And so what really the SNR is the difference between the signal power and the noise power. Okay, so now if we go back to this discussion, if my signal level's up at 0 dB, and this gap now is my SNR. This is the SNR of my signal versus thermal noise. Signal power minus noise power. So now if I come in and now I want to pass all this through an analog to digital converter, then what ultimately I've got a couple of design choices. I can design the analog low-pass filter, and I got to pick a sampling rate, and I got to pick the number of bits B. So again, if I can match if my SNR here with respect signal level versus thermal noise matches the SNR of signal level versus quantization noise, then all my bits are good. Another way of saying it is if I tell you that the SNR of signal level versus thermal noise floor is, say, 60 dB, then I know I got how many good bits if I quantize? 9 or 10, depends on C naught. Right? So if C naught were 0, I'd have 10 bits. Depends on C naught. So I can work this formula both ways. If I know the SNR in the system, it tells me how many bits I can reliably get, and any bits beyond that are just noise. Or I can say if I have a certain number of bits, it tells me what's the SNR of the signal level versus the quantization noise. So either way, I can work this formula either way. Now on the dual of this, which is digital analog conversion, and again, we talked about this in lecture 7, interpolation and pulse shaping, quite a bit, the first block. So the first block is convert from discrete time to continuous time, and then through interpolation, and then we clean up artifacts by using an analog low-pass filter. But it turns out that this analog low-pass filter in the D to A converter has the same specification as the A to D converter, as the analog filter in the A to D converter. So you build one, you get the other one. Problem is, building this is not so easy. So let's talk about why that is. So if I wanted to design the low-pass filter, then I know my stop band frequency has to be less than half the sampling rate. So the maximum frequency of interest, so we know that this is just a side effect of the sampling theorem. Sampling theorem says that Fs is greater than 2F max. And so for the role of the filter, the maximum frequency is the stop band frequency. That means that our sampling rate has to be greater than 2F stop. That means that F stop has to be less than 1/2 S, or half Fs. Just a side effect of the formula for the sampling theorem. We know we have a 10% transition band between pass band and stop band. So the pass band is 0.9 of the stop band frequency. Pass band frequency is 0.9 of the stop band frequency. In lecture 8 on quantization, we also derived that, this, again, just from this same graph up here of signal level versus thermal noise floor, means that if we think about quantization error, the stop band attenuation should be equal to the noise floor. We want to push down any frequency above the frequency range of interest, which is up to the pass band. We want to really push those frequency contents down into the noise. So our stop band, so it doesn't affect us when we do the quantization in the A to D conversion. So the stop band attenuation is going to be equal to the SNR. And that SNR is dependent on the number of bits. Right, so the SNR is this. Right, so it varies with 6 dB per bit. I increase the number of bits, I increase the stop band attenuation. Now, the flip side of this is that in the pass band of the filter, over the frequencies I care about, I want to capture those frequencies down to the resolution of a least significant bit in my quantizer. That's one step size. So what I want to do is make sure that over the passband frequencies, the passband ripple is nothing bigger than the step size. We want to be that accurate to the least significant bit. Now, so what is the step size as a function of number of bits? Well, it's right here. So first, it's the range of the quantizer and voltage. This assumes just a mid-rise. So here the voltage range is minus M max to M max in the quantizer, at the quantizer input. Number of steps is number of levels minus 1. So the number of steps is the range in voltage that I support at the input to the quantizer divided by the number of steps in the quantizer. And then to make it a filter spec, I convert these linear units into dB by 20 log 10. Go ahead.
So this is to limit the ripple in the passband?
Correct. Or if there's no ripple, it limits the deviation over the passband. So if it were Butterworth, then it wouldn't ripple. It would just be monotonic. But it's the deviation over the passband.
I know you said that C naught is a constant.
Mm-hmm.
And is there any way to estimate, like what would it look like on a diagram? Like you know how you have SNR up there? Like what would C naught look like on like a diagram?
You go at this two ways. One is the derivation in lecture 8, which is C naught's dependent on the max voltage on the quantizer and the average, which is a quantizer setting, and then the average power of the signal that's input to the quantizer, which is application dependent. So this varies quite a bit. So in audio, this is 1 to 2 dB. Another way you can look at it is to use, for communication systems, use plots of simple error rate versus SNR. And you can figure what C naught is for a certain target bit error rate. And there's a midterm question on that one. So for QAM, C naught's like 4 dB, something like that, in that example. So it's small. It's usually less than 6 dB. It's not, in this, there are some cases, okay, so there are some cases it's more than 6. So in DSL, this thing was like 11 dB. It was big. So you had to have a lot of signal power to get any bits through the system. So I guess it can be bigger than 6. But for what we've seen in the class, this is usually 1 to 2 dB for audio, 4 dB for QAM, single carrier. Yeah.
On that midterm, there was that midterm question where you had to do this with QAM and they used 3 dB per bit instead of 6 dB per bit.
Right.
I kind of understand that has something to do with the fact that you're representing, you can, in the same signal, since they're out of phase, you can represent 2 things at once. But I think you don't quite understand why that would be less SNR, because I feel like you're transmitting more. So is because you have such more power in the signal that essentially gives you a higher SNR and you don't need to.
Okay, so if you think about QAM, so the question was QAM. If you think about QAM as two-dimensional pan,
Yes.
then it helps make this a lot easier. So what I have in QAM, so consider for QAM. So if I have 1 bit in the in-phase component, I have 1 bit in the quadra component. And they're orthogonal to each other.
Yes, they don't see each other.
This is the huge thing. On the transmitter side, they're going to be orthogonal. Now that may be less so at the receiver, usually some distortion. But at the transmitter side, they're orthogonal to any reasonable degree of accuracy. Okay, so they're going to be orthogonal, and it means that if I have 6 dB, let's just let C naught be 0 for a minute. So if I have 6 dB of noise power, then what does that mean? It means I get 1 bit in the in-phase direction and 1 bit in the quadrature direction. I get to squeeze in 2 bits for 6 dB.
So really, the reason that you only need half of the SNR per bit is because the fact that the noise is split between.
That's correct, and the noise is orthogonal. That noise is split between the two. It's pretty cool. Yeah, so for QAM, it's 3 dB per bit. So this formula is for one channel. So this is for one channel quantization. For 2 channels, it'd be 3 dB per bit, not 6. 2 orthogonal channels. Okay, yeah, so back to the design of the analog filter. Now this is really bad news because as the number of bits increases, the stop band attenuation increases and the passband deviation decreases. So it drives up my filter order like crazy. The transition band hasn't changed. The locations of passband and stopband frequencies haven't changed, but this added, increase. So every bit that I want, I have to do another 60 dB increase of the stopband, and I get a decrease in the passband. So I get huge filter orders very fast. For even 8, 9, 10 bits, this filter's order is really high. So we can alleviate this with noise shade feedback coding, or we call it sigma delta. We call it lots of different things. But using feedback at the end of lecture 10, we could really reduce all the analog continuous time components down to sample and hold. And the rest of the components are clocked. Much easier to design than having a bunch of RC, RLC sections and so forth. So again, this approach for A to D conversion and D to A conversion, as shown here, is the theory. It can be implementation if I don't have many bits and I don't have a very high sampling rate. I can actually implement it as these block diagrams would say. But for a lot of bits or a high sampling rate, we're not going to implement according to these block diagrams on this slide. But this is the theory, and it's a good starting point. Okay, let's go on to some multi-rate systems. So this is right out of previous slides. So this, you can look at this as in an audio data converter or pulse shaping in a communication transmitter, same block diagram. So this is the notion of changing the sampling rate only through discrete time operations, which avoids having to go from discrete to continuous, then continuous back to discrete. So here we're going to change the sampling rate by a factor of 4 by upsampling. And just to review what upsampling is, so upsampling takes an input signal, and for every input value, it copies it from input to output, and then it appends L minus 1 zeros. In this case, L is 4, so 3 zeros. Next sample comes into the upsampler, it gets copied to the output. I append L minus 1 zeros, and I keep doing this over and over again. So there's no multiplication addition operations, it's just memory moves and a bunch of zeros being inserted. But on the output, I have 4 times as many samples as I had on the input. This means that my sampling rate is increased by a factor of 4, or more generally a factor of L. Now, by inserting these zeros, we've introduced some artificial high frequencies, because suddenly I have this transition from some value, and suddenly it goes down to 0, and then suddenly it stays 0. That's a really crazy change. That's a lot of high frequency components. And then at the end of this, I have another crazy change going from 0 to some other value. So these are a lot of artificially high frequencies being introduced.
I've always been kind of slightly confused about upsampling and downsampling in general. Is the main purpose of them just to change the sampling rate that you see on like a different device, so that 2 different devices that are operating different sampling rates are compatible? Is that like kind of the idea?
Well, the idea here is that this is a fixed sampling rate change, so it's not adaptive. It's not adaptive to some other device or some other format. So this doesn't. So you have to be pretty confident that your clock is what you need. All right, so this is a fixed change. So this is So for example, we looked at this in communication systems. This was the symbol rate, and then we had 4 samples per symbol. And then this became the sampling rate for the communications transmitter. So it's fixed. It's a fixed parameter.
But it is essentially kind of like a compatibility layer. Like
Correct.
to make it so 2 devices that are operating at different rates.
Or 2 subsystems is probably a better way to think about it. So 2 subsystems in the same system operating at 2 different data rates, and those data rates are related to by a rational factor. And so this is an integer factor. This is increase by a factor of L. Downsampling decreases that rate by a factor of L. But if we combine upsampling and downsampling, we can get any rational rate change.
And so, like, if for some reason you had control over the whole system and you were sampling at the original, at that, like, the sampling rate, the second one, if you were sampling at the original sampling, that sampling rate in the first place, you would not need the upsampler in that case. Is that correct?
The sample rate is equal to the sample.
Yes, that's right. Then you wouldn't need it. L is 1. in that case. Upsampling by 1 doesn't do much. Doesn't do anything. Just copies input to output. That's all it does. All right, to kind of clean up these artificially high frequencies introduced by inserting these zeros, we'll filter. Not a surprise. And this filtering will connect the dots. So this filtering, it depends on how it's designed, but it certainly will connect the dots. And if it's designed right, we don't change at all the original samples that came through on the input to the upsampler. So if we choose the pulse shape or the impulse response correctly, we don't at all change what we started with. But instead, we fill in values between those values that we know. Go ahead.
So, like, whether or not we touch the sample that doesn't belong to us, that's determined by the delay of the pulse shape filter, right? Or I guess the window.
What happens to these samples after filtering depends on whether or not I have zero crossings in the impulse response at integer multiples of L. Because what happens is if I look at the output of this one, it's going to be this upsampled signal filtered, right? So I'm going to take the output of the upsampler and I'm going to filter it. So I'm going to convolve the two. So in order for the original values to stay unchanged, then I need to make sure that as I do the flip and slide, across this signal, that means when I'm here, that means that the filter that's over here, the filter coefficient better be 0. I don't want any contribution of this one, and these are already 0. So if I so here's here's a filter, I suppose. In fact, we know the sync pulse is the ideal interpolator here, right? The sync pulse is the best we can do from an LTI point of view. It's an ideal low-pass filter if it's two-sided sync. Anyway, so here's just something. So if I have 0 crossings every 4th value, and I do the flip and slide of G of M with the output of the upsampler, and as I flip and slide, the only contributions at this point here will be from where I got it from above. Because 4 samples later it's 0, and 4 samples later it's 0. So I don't get any contribution from these other original values coming out of the that went into the upsampler. Likewise, if I'm looking here at index 4, and I'm flipping and sliding, then contributions here and here are zeroed out if I have this shape G of M for my impulse response.
When you say the sync is the best shape to do the interpolation, that was the sync from the discrete time.
Correct. It's also it's a version of the sync in discrete time. That's correct. Because remember, the filter we want here is ideal low-pass filter, and its cutoff should be pi over 4. Pi over L. Right, so the cutoff frequency here pi over 4. Pi over L, more generally. And yeah, if we could have a two-sided sync, we'd love that. That would be the ideal low-pass filter. We just can't build it. Right? Good. Okay, so this is to enforce, why is it pi over L? It's to enforce the sampling theorem. Because what happens is, if this sampling rate, let's say, go back to an audio example, say this is 40 port, let's say, so let me go to audio for a second. Let me scratch these communication systems. So let's do audio, for example. And if I upsample by 4, I now have a new sampling rate, which is 4 times higher. But the original sampling rate means that I only capture frequencies below 22.05. kilohertz. This is standard sampling theorem. So although I'm sampling at 176.4 kilohertz, any frequencies that are above 22.05 kilohertz are artificial. They weren't there. So if you think about what does that mean? So if I think about, so this captures F max is 22.05 kilohertz. Okay, so where is F max here? So here's omega max. So it's going to be 2 pi F max over the new sampling rate, which is 2 pi 22.05 kilohertz over 176.4 kilohertz, which is pi over 4. And more generally, it's pi over L. Okay, so any frequencies that are above pi over L are artificial. They were introduced by the upsampling operation. They did not exist prior to upsampling. So we want to filter those out.
So in your signal, since the highest frequency that you have still is 22.5
05, yeah.
kilohertz, then I guess the question goes back to what was the purpose of upsampling? Because you have more frequency that could be artificial, so you're not getting rid of those and you're kind of introducing noise in your sound.
Well, you're introducing some artifacts which you then clean up. So you have some. So why do all this upsampling? First of all, we do it to match some sort of needed sampling rate. So in the communication system, we go from symbol rate to sample rate. For an audio converter, what it allows us to do is now I've created all these frequencies that I can't hear. I can't hear frequencies between 22.05 and this max and 88.2 kilohertz. So this captures So the good news is, from a data converter point of view, it gives me all these frequencies to put quantization noise in that I can't hear. And later I'll just low pass filter them away. Kind of fun. And this one, for other reasons, we just need to match sampling rates. We need to match it to a target sampling rate. That's why we upsample. Upsampling by 4, if it were an image, means that I would have 4 times as many rows and 4 times as many columns as I started with. So I'd expand the image by a factor of 4 along the rows and 4 along the columns. Right, so just to get to some other resolution that I really want. Okay, and then these numbers that I have up here that are kind of, I guess they're just subtle here. The 1 means for every one input sample, I get 4 output samples. That's all that those numbers mean. And for every 1 input sample into the FIR filter, I get 1 sample out. Okay, now let's do the dual of this. Oh, sorry, let's do the efficient implementation, then we'll do the dual. So the efficient implementation, this is from a communication systems point of view, this is in the transmitter. And we worked through the derivation of this lecture 13 slides. So we can take, and it kind of makes sense because if we look at the cascade of this upsampler and FIR filter, the FIR filter ends up multiplying by 0 half the time when L is 2 and most of the time when L is greater than 2. We're wasting lots of operations here. So we can rewrite this as a polyphase filter bank, and now what comes in, all the filtering is being done at the lower sampling rate. So from a communication system point of view, the rate over here would be the symbol rate, and the output would be the sampling rate. So in this block diagram on the left, the filtering is done at the higher rate. But in the polyphase filter bank on the right, all the filtering is done at the lower rate, at the symbol rate. So I have just as much filtering to do. I have just as many coefficients to apply. But I do them at a lower rate, so I get a factor of L savings in the number of multiply accumulates per second. And if you notice that the upsamp, it's sort of an interesting, sort of a switch, because I'm doing the filtering at the symbol rate, and then I do this periodic read, known as a commutator, to do the rate change. Good.
So, like, in that thing, that commutator, what's going on there is that every time you take a sample, you take the sample from the next filter.
Correct.
And that will allow you. So the job of each filter would be you have one filter whose job is to sample like 0.0, one filter whose job is to do 0.1.
1. So these are polyphase, and they each have different delays. So this does index 0 on the output. This does index 1 on the output, and so forth. So I pull them off in order. So I start up here. I start with the upper branch, and I work my way down. So I first pick off. So I go this one, and then I do the second one, and then finally the last one, and then I start over at the top branch again. So I do it in a repeated pattern, and you kind of see that here. Right? So here is, you know, nth symbol. If I'm thinking about communication systems, this is the nth symbol and the 0 sample. Little m is 0. This is the nth symbol. Little m is 1, and then finally it's the nth symbol with index, sample index L minus 1. And then I start over again. So the filters run in parallel at the symbol rate, and then I just pull off the output of each filter in order to get the stream at the sampling rate.
So creating this bank of filters only helps when you can multiply by 0.
Well, you are. Well, remember this. I'm taking this cascade of upsampling and filtering, so I know that I'm going to be doing lots of So I know the structure of the signal coming here, right? So this is lots of zeros. You're right. This doesn't. If I didn't know that, it wouldn't make much sense.
So if the order of the filter is bigger than n, then all of your filters in the filter bank will have more than one coefficient.
That's correct, right. So the observation is if the impulse response of the original FIR filter is of length L, then I just have one coefficient for each polyphase filter. If the length of this FIR filter G of M were 2 times L, then I'd have 2 coefficients in each polyphase form. Because I have capital L polyphase filters, the number of coefficients in each polyphase filter will be determined by the number of coefficients in the original FIR filter in the cascade of upsampling and filtering. All the coefficients in the FIR filter have to find a home in one of the polyphase filters. I have the same amount of math to do in terms of multiply adds, but the good news is in the polyphase version, I do all that math at the reduced rate, and hence the factor of L savings. And then I have an additional degree of parallelism. I have also L degrees of, I have another, beyond the savings, I also have my L polyphase filters could be run in parallel if I had the target architecture to do it. So it's another factor of L savings in terms of speed.
So since you're processing everything at the low sample rate, that means that the commutator, like for each iteration of those polyphase filters doing one sample, that has the time to go through and sample every single one.
Correct. During one symbol period, I go through and I get one value from each of the polyphase filter outputs to get my L samples for that symbol period. That's right. All right, now let's do the dual of this, which is the decimation. So we're going to decrease the sampling rate by the same amount, or by some integer amount, not necessarily the same amount. So I have, so this is another sampling operation, but now I'm going to sample at, I'm basically going to change the sampling rate. I'm going to reduce it by a factor of 4. Now, if I reduce the sampling rate by a factor of 4, I can introduce a lot of aliasing. I'm only keeping 1 out of every 4 samples. So I need, what kind of filter before that? Anti-aliasing filter, that's right. So this is my anti-aliasing filter. And it has the same design spec as the FIR filter in the upsampling case. Yes. Next slide. Okay, so it's the same cutoff. So it's an aliasing filter, and the cutoff frequency is pi/4. This is on the receiver side if it's a communication system, that's right. Yep. It's pretty close. Right, so this in the communication systems, so in communication systems, right? G of M is what filter? The match filter, that's right. So it's going to be a low pass, right? So it's matched. So anyway, more generally, this is a low pass filter, and it's going to enforce the sampling theorem, because again, any frequencies at or above 1/4 of this max frequency will alias. The same reasons as we derived for the upsampling case. So downsampling, basically takes L samples in, keeps the first one, throws out the rest. Decreases the sampling rate by a factor of L. So again, here's the input to the downsampler. I take a block of L. Now in my case, L is 4. So I take my block of L samples. I keep the first one and I throw out the rest. Next block of 4 samples comes in. I keep one and I keep the first one and delete the rest. That's your output of the downsampler. And it has a polyphase form. The polyphase form, so we look at this, kind of makes some sense. Why there's a polyphase form? If I look at what do I take? I have a filter, an FIR filter, but I only keep 1 out of L's outputs. I throw out L over 1 over L samples, or I discard the outputs, L minus 1 over L percentage of the time. So why calculate what I'm not going to keep? Why am I bothering? Well, no. Oh, the filter can have its own memory. I don't care what happens in the filter. But as far as the upsampler is concerned, why am I even bothered? So it's okay that I keep my delay line up to date. That's fine. But instead of doing the math, why am I bothering calculating what I'm not going to keep? Reduce implementation complexity big time. So it leads to another filter bank structure. And you can see it by working. So what do I need? Here's Y. So if I look at Y, so I look at the value. So Y of 0, Y of 1. If I backtrack from Y of 1, the value that I need is the Lth value coming out of V, because I only, remember, for every block of L samples, I keep the first one, throw out the rest. So Y of 0 is V of 0. Y of 1 is V of L, because all the other values get discarded in between. And I do the basic, FIR difference equation, flip and slide, the FIR coefficients, H about the input, S, and I get this form. But I only need to do this every L samples. I don't need to do this any more often than that. So if I work backwards, or work toward a block diagram, I have the input S come in, and I use what's called a distributor. So it's the dual of the commutator. So I distribute the signal, so S0 goes up here, S1 goes here, all the way down. I send it through a bank of polyphase filters. And because I have the distributor here, all I'm going to do is add up all the outputs of the polyphase filters, and that's my answer. So again, I'm running the filters at the lower rate, not the higher rate. So on the one on the left, the filter runs at the high rate. For the polyphase case, the filters run at the low rate. And again, I'm only computing the values I need. And I also have L degrees of parallelism, and I can exploit that further. So I get another factor of L. I get a factor of L savings here because I only compute 1 out of L samples, just the one I need. Don't bother computing the ones I'm going to throw away. And then in addition to that, I have these L polyphase filters in parallel. And so if, again, my target architecture, such as an FPGA, could handle this, parallelism, I get another factor of L speed up by doing the polyphase filtering in parallel. I know we're at time, so what I can do is for those that need to leave, that's fine. We'll just keep recording, and you can look at this at your leisure. That's fine. I know some of you have classes, so go ahead and don't miss your class at 12. And we'll just keep going. Give a short pause to let you leave.
So because of the parallelism, you get your output rate is 1 over L times the...
That's right. That's right. So going back one, the reduction in the rate, I'm reducing the sampling rate by whatever the rate is by a factor of L. All right, so let's go into communication systems and knock this out. So for communication systems, we had a message that we want to send. Information could be voice, music, image, video, data. The information is low-frequency information, the content centered at DC. On the transmitter side, we'll have baseband processing to enforce ultimately what frequencies we're going to ultimately use for transmission. And so we start back at baseband by low-pass filtering to start enforcing the transmission band. And then the baseband, after baseband processing, the carrier circuits will then do whatever is needed to go from this baseband discrete time, this baseband signal to some other carrier frequency. So the carrier circuits may be as simple as a D to A converter and a power amplifier, possibly in a filter that follows the power amp. Or it could be more complicated than this. It could be a series of up conversion stages to RF. Lots of possibilities. On the channel is going to attenuate and also spread the signal in the time domain. The spreading is due to convolution. And the longer the distance of that propagation through the channel, the more loss we're going to have, the more attenuation we'll have, and the more spreading that we would have. At the receiver, we have a lot of work to do. So we've talked about a lot of these. We want to have a receive filter, which is analog continuous time to enforce the transmission band, generally bandpass. Carrier recovery to figure out if there's upconverted transmission on the transmitter side, then we need to figure out what the carrier frequency and phase are. We're going to have, again, if we're upconverted, we have to have some sort of down converter. And typically in RF, we're going to have 2 stages. Sometimes you need one, depends on the RF frequency. We know that because of the attenuation is going to vary with distance and some other factors, we're going to have automatic gain control to boost the signal at the receiver before we go through A to D conversion. Go ahead.
Carrier recovery and symbol recovery symbol rate recovery, those are 2 separate things.
They're 2 separate things, but they can use the same kind of method. So in the carrier recovery, let's say we have an RF carrier like 2.4 gigahertz and the error maybe is 1%. So we have a very small range where that thing could be. For symbol recovery, we have a symbol rate, whatever it happens to be, could be 1,000, could be whatever it is, 2,000 hertz. And we know that in the baseband component, we know at least because of pulse shaping, half the symbol rate will be there. So we can lock onto 1,000 hertz. So you go through a squaring device and get that 1,000 to 2,000. Okay, so for the symbol rate, we tend to lock onto half the symbol rate. And for the carrier frequency, we just lock on directly to that carrier. That carrier is present.
So they both kind of, they serve the same purpose, but they, because of the way that the signal, because of the way that the signals are being transmitted, we have to do it slightly.
Well, they're very different frequency ranges, typically, right? So there's two different types of carrier recovery. There's going to be the RF. If it's RF, it's going to be a very high frequency. Then you also want to recover, if it's QAM, you also do another round of recovery in discrete time after A to D conversion for the QAM demodulation. That's a low frequency carrier. And then the symbol clock's even typically lower frequency than that, than the carrier, than the QAM carrier. But in the end, you're trying to pull out a narrowband signal that's a clock frequency out of some signal. So preemphasis is a way to do that. And then finally, after we go through all the receiver, so that's all the carrier circuitry. And after the carrier circuitry, then the baseband processing would be extraction and enhancement. So this would be additional filtering, decision, thresholding the nearest symbol amplitude values. So this is lab 6. So this is the baseband part. This is lab 6. This is just the expansion of that into a block diagram. This is right out of lecture 15 slides. So we have bits come in. We get symbol of bits. We look up from that using that symbol as a index into a lookup table unsigned. Get our in-phase and quadrature amplitudes, and then go through baseband PAM in 2 channels. So this part is baseband PAM, followed by up conversion. And subtracting the 2 up converted PAM signals so that we use the same transmission bandwidth for 2 signals instead of 1. And so that's where the carrier frequency will come. So in the receiver, we're going to have to figure out what the QAM carrier frequency and phase is, which is a low frequency value. We also want to lock onto the symbol clock that's being used here. So here's the symbol rate. So here we're at the symbol rate. And again, because of the pulse shaping, that we know we can lock onto half the symbol rate. Depends on the pulse shaping, but we know half the symbol rate should be there, regardless of the pulse shaping. Okay, so that's the transmitter side, baseband transmitter side. Baseband receiver side looks a lot like it. So on the baseband side, I'll have an equalizer. This is after the A to D. And then the QAM demod. So in addition, we know there's also other things off to the side, symbol clock recovery, carrier detection, and so forth. And there's, prior to this point, prior to here, there's going to be automatic gain control and A to D conversion. And we can just, I guess, include those in the carrier circuits. So demod here, so we have 2 channels come in, and we simply do PAM down conversion, 2 channels of that, 1 in phase, 1 quadrature, and then finally get the 2 symbol amplitudes and look up the nearest point in the constellation map. So the rest of the block diagram simplifies nicely, it turns out, very nicely. So the rest of this block diagram, which is the carrier circuits, the channel transmission medium, and the carrier circuits on the receiver side, can collapse down to a very nice model, because at the baseband output, this is discrete time, the way I've described it in these slides. This baseband input is discrete time. What's in between is a lot of complicated processing and design, but we can reduce it, much to the disappointment of analog IC designers, down to 3 very simple blocks. Obviously not telling the whole story. This is a very simple model of a very complicated set of subsystems. So I have basically gain. This is the attenuation. It could vary with time. I have memory in the channel. And frequency selectivity. And last but not least, are additive noise, at least thermal noise. And so this is now it's all in discrete time. So this whole communication system, and you've done this on homework, can be implemented completely in discrete time. MATLAB, LabVIEW, whatever you happen to use. We mainly use MATLAB in the class. And That's it. It's a very simple channel model, but you can simulate pretty well your baseband processing with this very simple channel model. And that channel model is in completely discrete time. So we call this a baseband channel model. A more complicated model, we'd have to include all the analog circuitry, SPICE simulation, whatever. Okay, last slide here is the QAM signal quality. This is, we derived this in lecture 16, also in 15 slides. And this was the idea that if, once you understand 16 QAM, you can do any QAM constellation that's regularly spaced or uniformly spaced between points. So I have 3 constellation types. I've got interior points, I have edge points that are not corners, and I have corners. And knowing that, we can derive the probability of symbol error, knowing how many type 1s we have, how many type 2s we have, how many type 3s we have, assuming equally likely transmission of all the symbol values. And here's the final answer for 16 QAM down here in the box. So I get, it's two-dimensional, so I get a term that depends on the Q function and the Q function squared.
Could you remind us what the Q function represents?
Yeah, the Q function is the area of a normalized PDF over the tail. And it's normalized Gaussian. Here, so it's this tail. It's the area under the tail.
So the Q function really represents the probability of error.
Correct. That's right. For one tail. So it's when you get in trouble in one direction. If you get in trouble in 2 directions, then I need to sum up 2 tails. So it's 2 times the Q function. And then in all these symbol error calculations, the argument to the Q function is proportional to the square root of SNR. So if SNR increases, the Q function decreases. So higher the SNR, the lower the symbol probability, and it's a lot. It's a big drop. A little bit of improvement in SNR, and it's a huge drop because the Q function is more or less an exponentially decaying signal with respect to SNR. So we get a little bit of increase in SNR, a huge decrease in symbol error probability.
So the D increase, does the probability of error increase or?
That's correct. So you've got 2 parameters that you can control in your system design. That is D and the symbol time. So D is half the constellation spacing, right? So this is 2D, and the symbol time. And you're really stuck with the noise in the system or the channel, the noise in the system and the channel. Actually, you're stuck with that. All right. So if you increase D, it means what? You increase the peak power and the signal, the average power and the peak power in the transmitter. So you crank up the power in the transmitter, and that's going to give you better SNR by the time you go through the receiver. Go through the match filter and the downsampling. And so by the time you hit the decision device, you have increased SNR because you've increased the signal power back to the transmitter. You cranked up the volume, whatever. So you've got, more signal power. The other option is to, so that's just going to be more power at the transmitter side. And on the symbol time, you can certainly increase the symbol time, and that will increase the SNR because you get longer correlations in the receiver for your match filter. So that's going to increase your effective SNR. But what's the problem if you increase the symbol time? You lower the bit rate. So if you increase the symbol time, you decrease the symbol rate, you lower the data rate. Okay.
The Q function is the probability of error. And wouldn't that increase when you increase the noise? It's like inverted.
So the Q is decaying. So Q looks like this. Q is monotonically decreasing. Not so accurate there, but yes, it's faster than.
We
Correct. So that's right. So you want you want a low. So for us, we want a lower symbol error probability. We want a lower chance of a symbol mistake.
Yeah.
So what we really want is we'd love to have, so when x increases, if I have an increase of x, so if x goes like this, then q goes like this, right? Goes way down.
Okay. You want a low Q. You want the arguments inside to be high.
And the q function is approximately e to the minus, well, it's a little more complicated. So x in this case is just x, but for our case, we actually would use it, x is the square root of s and r, or proportional to the square root of s and r. And what this really means is this decay is roughly, if x, so x here is square root of s and r, but if I think about it in s and r terms, it's it's exponentially decreasing in s and r. That's a big drop with a little bit of s and r improvement. That's it. Thanks for staying over. Andy, thank you.
No problem. No problem.